Today, we will be learning how to determine the internal shear and bending moments at any location along a beam, and how we can use these to derive the equations for shear and bending moments. These equations are important in structural design because they allow us to find the maximum shear and bending moments within our beam. And this can tell us whether the beam is strong enough for the application, and we would also know where along the beam is failure most likely to happen. So it's very important to know this stuff. When you break it down, the problems can be very simple. So let's start by looking at the simply supported beam here. It's nice to get familiar with something that's a little bit simpler before moving on to a more complicated loading system. So for this beam right here, the first step, as always, is going to be determining the support reactions. So we can see that we have a roller here, which provides a single force perpendicular to the beam. And over here we have a pin support, which is going to provide a vertical reaction and a horizontal reaction. And ahead of time, I've already provided our positive sign convention right here. So I will be using this for both problems. To start, we'll apply the equations of equilibrium. So we know sum of the forces in X are equal to 0, but it's really simple because we only have one force in the X, and we know all our forces must be 0, so we can just ignore this altogether. Next, we'll move on to some of the forces in Y, which are also equal to 0. So, based on this, we know 0 is equal to, and now we can list all of our forces in Y here. So we'll have a force at A going in the positive direction, take away 10, which is our uniformly distributed load. Actually, I'll include units as well, just for organization. So we have a force at A pointing up, and we're subtracting, because our force is going down here, subtract 10 kilonewtons per meter over a distance of 5 meters. And then we will add our vertical force at B as well. So these three here make up all the forces that we have to deal with. And so then we get the equation. So 10 kilonewtons per meter times 5 will get us 50 kilonewtons. And then if we add all of this to the other side, we get 50 kilonewtons. So I moved everything here to the other side, is equal to FA plus FB. And so there we go. We have one equation with our two unknown support reactions. And we could go ahead and use sum of the moments equals 0. This would be our second equation, which could let us solve for either of these two forces. However, we can just keep it simple for now because we know that this beam is symmetrical. And so the force at A is going to be equal to the force at B. So really, we know that 50 kilonewtons is equal to, instead of FA plus FB, that's the same thing as having 2 FA. And then we can simply divide by 2, and then we get FA, which we know is equal to FB due to symmetry, equals 25 kilonewtons. So there we go. And I'll mark that here in blue. Actually, I'll use green, just to show that these are values that we've calculated. 25 kilonewtons, 25 kilonewtons there. Okay, so these are likely problems you've seen before. We found our support reactions. So now this is where the internal forces come into play. So to start, I am going to make a cut throughout the beam. And that cut, you can literally think of as we are splitting the beam in half at a certain point. So before we go on to finding the maximum shear and bending moments, let's start with something a little bit simpler and say, let's find the shear and moment at a specific point. In that specific point, I am going to make 1 meter from the left side of the beam. And so here you can see I've already labeled the left side of the beam as x coordinate 0. So then I'm cutting it at x equals 1, which is 1 meter away from the left side of the beam. So now we can shift our focus down here. And so all I've done is I've actually taken this little slice of the beam, and remember, we've cut this in half. So I've taken this little slice and moved it down here. And what this does is it allows us to shift our focus to this specific point in the beam right here, which is what we're interested in. Right now, we want to find what are those internal shear and bending moments at that specific point. So remember, you always cut the beam at the location where you're interested in the internal forces. So, in this portion of the beam right here, we still have our uniformly distributed load, 10 kilonewtons per meter, and we still have our vertical support reaction of 25 kilonewtons. But now, this right here is not balanced, and we know that because right now this pin is the only support supporting this load right here. If this were to happen in real life, this is a pin right here, and this beam would just rotate down like that because there's nothing to resist that moment. We've lost our support over here. So instead of drawing the rest of the beam, we can replace this section with an equivalent shear and bending moment that essentially represents the way that this part of the beam is supported by this side. And if that doesn't make sense right now, just bear with me because I think it'll help when I draw it out. So let's show we will have shear and a moment force. And so all we've done here is we've replaced this section of the beam with a force, a shear force, and a bending moment. And so now we want to be able to solve for these, and then at that point we've essentially found that internal shear and internal bending at that location of the beam. And these are important quantities to find because oftentimes in structural design, we need to make sure that our beam is able to withstand these internal forces. If that moment is larger than the capacity of the beam, our structure will fail. And so that is why we want to be able to have a good understanding of being able to find these forces. Which remember, these diagrams are the same thing. We're just shifting the focus to where we cut our beam. We're shifting the focus to one specific point within the beam. So enough talking on my part. We can go into finding that shear and bending moment that we have here. And we're just going to do it in the exact same way that we found our support reactions. We're just going to apply the equations of equilibrium. So to start, sum of the forces in y are equal to 0. So then 0 is equal to 25 kilonewtons. That's this right here. Take away 10 kilonewton meters. Sorry, 10 kilonewtons per meter. And I should label this distance as well. Remember, we took our cut. Ooh, getting a little bit crowded there. Let me just label it right here. So remember, this is a distance of 1 meter because we cut our original beam at a distance of 1 meter. So that's transferred over down here. So we're subtracting our uniformly distributed load, 10 kilonewtons per meter acting over a distance of 1 meter, plus, let's label this force as V. V will be our symbol for shear. And let's label this moment as M. V and M. So we have 25, take away 10 kilonewtons per meter times 1 meter, plus V. And so now we can simply isolate V. So we have 0 equals 25, take away 10, because 10 times 1 is 10, plus V. So then, well, this we can just write as, that would just be 15, and we move 15 to the other side, and we get negative 15 kilonewtons is equal to V. Okay, so the negative sign in this case actually means that this arrow we initially drew for our shear is actually in the wrong direction. We have negative, so this direction, downward, 15 kilonewtons of shear. So let me just well, I'll keep that there. Let's go back to green for what we found. So let's go down 15 kilonewtons. Okay, and now it's time to find the moment. So now we can take some of the moments around A, and remember A is just this, the location of this support right here. So we have A. Some of the moments around A is equal to 0, and then we know that 0 is equal to, now using this sign convention we have here, we can write out our moments on this side. So we'll have our uniformly distributed load. At A, that's causing a moment that's going clockwise instead of counterclockwise, so we'll have a negative moment. Negative 10 kilonewtons per meter times 1 meter. So this right here gives us the equivalent force. We have 10 kilonewtons per meter times 1 meter. So we have negative 10 kilonewtons acting at a distance of 0.5 meters. And why is it 0.5 meters? Well, that's because the equivalent point load, if we were to transfer this UDL into an equivalent force, that force would act right through the middle of that UDL. And the middle is half of this distance right here. It's half of 1 meter. We have 0.5 meters as our moment arm. So then we have the negative moment caused by this UDL right here, plus the moment that our shear is causing. Because remember, this shear, that is a force still, and it's a force acting at a distance away from that support. So we can add, because remember, this is going to create a counterclockwise moment, that's positive, plus V times 1 meter. This is getting a little bit crooked here, but bear with me. And then we also have to add this moment right here, which is also going to counterclockwise, plus M. So then let's just try to clean this up a little bit. We'll get 0 is equal to negative 10 kilonewtons per meter times 1 meter, that's 10 kilonewtons, times 0.5, so half of 10, negative 5 kilonewton meters, plus our shear, which is negative 15. Because remember, we want to, when I took V as positive because I'm using our original assumption that V is pointing up, which creates that counterclockwise moment. So whatever your initial guesses are for V and M, because I didn't mention this at the beginning, but you have to choose a direction. So shear, it's either going to point up or down. Moment is either going to be counterclockwise or clockwise. So you have to make your best guess, and then just stay consistent with it. You want to use those sign conventions because it will change these equations, right? I'm taking this as positive because it's pointing up. If it was pointing down, I would take it as negative. So back to cleaning this up, we have plus V, which is negative 15. So we have negative 15 kilonewtons times 1 meter. So that's negative 15 kilonewton meters plus M. And then we move these to the other side. Negative 5 take away 15 is 20. And then add 20 to both sides of the equation. And we get 20 kilonewton meters equals M. And there we go. So then I'll just label this for us as well. That's 20 kilonewton meters. And apologies for the whiteboard getting a little bit cluttered. I'll try to remember to use more space next time, just to make these stand out a little bit more. But to summarize, we now have found our internal shear and internal moment at a cut of 1 meter. And so, at first glance, this isn't very useful because at 1 meter, this point doesn't really matter to us. It's just a random point in our beam. We don't really care about these values, but this sort of sets up the framework for finding an equation for the shear and moment at any point along the beam. So, what I want to do now is I want to repeat this process, but instead of labeling that distance as 1 meter, what I want to do is instead let's go back. Let's go back to our cut. Instead of calling this distance 1 meter, because remember last time we took our cut at a very specific location. Now, what if instead of calling this a specific distance, we just label our cut at a distance of x, using a variable instead? So, starting over down here, we have our 10 kilonewton per meter UDL, and our distance from the support to where we cut. Because remember, where this beam is cut off, that's where we take our cut. Let's call this distance x. So now we have a variable, and so we can repeat all of these same calculations, but instead of using 1 meter for our calculations, we simply use a variable x instead. And this is crucial because now all we have to do is, instead of getting exact values for V and M, we'll get moment and shear as an expression of this variable x. And so then all you have to do is plug in an x value. I can plug in 1 meter, I can plug in 4 meters, 5 meters, 3 meters, and I can determine the moment and shear. Essentially, when we use x, we set an arbitrary distance. Because remember, moment and shear change as you move through x. So what this does is we essentially get an equation for moment and shear at any point along the beam. And that's really what is leading us to our ultimate goal of finding the maximum shear and bending moment. So I'm going to grab a chair because I'm getting to the lower end of the whiteboard. And so repeating the same process, we have our 25 kilonewtons acting right here. And remember, this is just the same support that we used in the very original scenario. So 25 kilonewtons, 10 kilonewtons per meter at a distance of x. Now, same thing. Let's include our shear and moment. So let's call this V, and let's call this M. So now we can take some of the forces in y equals 0. 0 is equal to 25 kilonewtons, take away 10 kilonewtons per meter, acting over a distance of x, plus shear. So then we get 0 equals 25 take away 10 times x, 10x plus v. And then we move these over to the other side and we get 10x take away 25 equals v. And this will be in units of kilonewtons. So there we go. We now have an equation for shear at any moment along our beam x. And so just to test this, we can plug in our x value of 1 meter. So let's plug in 1 meter. We do 10 times 1 meter, take away 25. So all I've done is I've plugged in 1 meter into this part of the equation. You get 10 take away 25 equals negative 15 kilonewtons, which is exactly what we got for our shear last time. So this equation now works at any point along the beam. And this is going to be very useful for finding the maximum shear and maximum moment. So I'll quickly work through the moment as well. So now, same process as last time. Some of the moments about, this is point A right here. Some of the moments around A are equal to, now we have, same thing as last time, negative 10 kilonewtons per meter over a distance of x. And then the moment arm is half of this distance, so x divided by 2. Just like that. And then we have, come on this side, then we have plus v, because positive moment, because it's going counterclockwise, plus v acting at a distance of x, and then plus our moment. So then we can simply sub in, so we'll get equals, and now we have negative 10 divided by 2, so that's negative 5 times x, so negative 5x squared, plus v, we can sub in what we found over here, 10x take away 25 times x plus m. And then let's simplify this further. Negative 5x squared plus 10x times x will give us 10x squared. Take away 25 times x, take away 25x plus m. And then now, oh, this should be a 0, because we know some of the moments is equal to 0. And now let's just move everything over. So negative 5x squared plus 10x squared, that's positive 5x squared, and then subtract that from both sides. Negative 5x squared plus 25x, right? We're adding 25x to both sides of the equation, so that goes away and then it becomes positive on the other side. Negative 5x squared plus 25x is equal to m. And that again will be in units of kilonewtons, kilonewton meters. So now we have derived both of the equations for shear and moment using a simply supported beam example. So now the only step remaining is we can go back to our original goal, which was finding the maximum shear and bending moment within the beam. And so, if you remember how to find the maximum, you may remember that you can take the derivative of an equation. So essentially, using this moment, for example, we will have a negative quadratic. So essentially, we'll have a graph that looks like this. And then we can see that at the maximum, the tangent or the derivative right here is equal to 0. The slope is equal to 0. So what we can do here is take the derivative of the moment. So let's go m equals negative 5x squared plus 25x. And then the derivative of moment over dx is equal to, now using the basic rules we use to take derivatives, we have negative 10x plus 25. And then let's set the derivative equal to 0, because we know at that maximum the derivative is equal to 0. Equal to 0. And then we get 25 equals 10x divided by 10, divided by 10. And then we get 2.5 meters is equal to x. And this right here is the location of the maximum moment, which we can see 2.5 meters is exactly half of the length of our beam, which makes sense because half of this distance is right through the center of the beam, which is where we're going to get the largest deflection. And due to symmetry, it makes sense that the moment is going to be straight through the middle. And now, moving on to the location of maximum shear, we can see that our equation for shear is linear, meaning that we won't be able to find the maximum shear in the same way that we found maximum moment, like we did here. Because we can see that for our quadratic, there is a clearly defined maximum where we can set the derivative equal to 0. But for a straight line, it's easier to actually just draw a graph where we can have x right here, and then we can have shear on this axis. So going based off of 10x take away 25, we see that at x equals 0, at x equals 0, we'll just be left with negative 25. So our line will actually start down here at negative 25. And then I'll just label this axis as well. 2, 3, 4, 5. We can see at the opposite end of the beam, at x equals 5 meters, we will have 10 times 5, which is 50, take away 25, gives us 25 kilonewtons of shear at the opposite end. So at 5 meters, we will have 25 kilonewtons of shear, like this. And so, just by looking at this graph, we can immediately see that the minimum shear and maximum shear are located at the supports, which are at the start of the beam and the end of the beam. And so through graphing it, this is helpful because it already gives us our values for shear. So we have negative 25 kilonewtons and then a positive 25 kilonewtons at this end. So now that we've covered shear, I want to quickly go back to the location of maximum moment and show how we can use this to find the value of that bending moment in the beam. So now, knowing that our location of the maximum bending is at x equals 2.5 meters, all we need to do is sum this back into the equation we found from the moment. So what that will give us is m equals -5 times 2.5 meters squared. As you can see, we have an x squared here, plus 25 times 2.5 meters. And then solving for this moment, I'll use my calculator for this. We have -5 times 2.5 squared plus 25 times 2.5 equals 31.25 kilonewton meters. So there's our final answer. And so now, to summarize how we went through this process, the main things I want you to remember is that when you're given a free body diagram of some loading condition, the first step is always getting the support reactions. And we started doing that by finding 25 kilonewtons on support A and 25 kilonewtons on support B. Then the next step was to take an arbitrary cut at a distance which we called x. And so what that allowed us to do is, when we have a distance of x, we can solve for that internal shear and internal moment in terms of x. And what that allows us to do is we can sub in any x value we want, and then we can find that shear and find that moment. And then that is very useful, because using those equations, we can find the location of the maximum moment and just simply sub that in to get the answer we're looking for. And so in any structural design, this would be a very important number. We need to make sure that whatever beam we're using is able to support a moment of this magnitude. And it's also important to know that that is acting at 2.5 meters, which is going to be right at this location, our beam right here. That's where our 31.25 kilonewton meters is acting internally within that beam. So I hope that clears things up. I hope you were able to gain some understanding of this. In the next videos, I'm hoping that I can make the whiteboard a lot less messy. This is my first video, so still learning through this process, but definitely going to work on just trying to deliver